Hey everybody, welcome back to AI Codecast. We're going to untangle another algorithm today.
Yeah,
And I'm really excited about this one.
me too.
It's called minimizing extra characters.
So imagine you're giving like a string of letters
Okay.
and a dictionary of words.
Mm-hmm.
You basically want to break that string
Right.
into words from that dictionary using as many letters as possible.
So like if our string is apple pie delicious,
Exactly.
and our dictionary has the words apple pie is and delicious.
Yeah.
We want to split it up into those 4 words.
Exactly.
It would have 0 extra characters.
Yeah, that's a perfect split.
Right.
But it gets a little tricky when you have longer strings
Yeah, I can imagine
and
it.
bigger dictionaries.
So where do we even start with something like this?
Well, we could start with brute force,
Okay.
just to get a feel for the problem.
So we would just try like every single possible combination of words?
Yeah, basically you check every substring
Yeah.
of the input string,
Mm-hmm.
and you see if it's in the dictionary.
Okay.
You keep track of which splits use the most characters,
Okay.
and then the one with the fewest leftovers,
Yeah.
that's our winner.
I can already see how this would be a problem.
Yeah.
With longer strings especially.
Exactly.
There'd just be too many combinations.
Yeah, so for a string of length n,
Okay.
you'd have to check 2 to the n possible substrings.
Right.
Which
This
is,
exponentially larger.
yeah, it gets out of hand pretty quick.
So brute force is good for just understanding the problem,
Yeah,
but not a real solution.
no. You need something a little smarter.
What do we got?
That's where dynamic programming comes in.
Ooh, I love dynamic programming.
It's all about breaking the problem down
Yeah.
into smaller, overlapping subproblems.
Right.
And solving each one just once.
I feel like dynamic programming is like that saying,
Yeah.
measured twice, cut once, but for code.
Exactly.
So how would we apply dynamic programming here?
So there's 2 main ways.
Okay.
There's top-down with memoization,
Okay.
and then there's bottom-up.
Let's start with top down.
Okay.
How would that work for this problem?
So imagine you have a function called minimize extra.
Okay.
It takes the starting index of a substring as input,
Uh-huh.
and it figures out the minimum extra characters needed to split the string from that starting index onwards.
Okay.
It explores different ways to break the string into words
Right.
from that point,
Okay.
and it calls itself recursively.
Oh, so it could get stuck in a loop?
Well, that's where the memorization comes in.
Okay.
Think of it like a detective's notebook.
Okay.
As we solve these subproblems,
Mm-hmm.
we write down the result in a table
Okay.
before we make a recursive call.
Right.
We check if that subproblem is already in the table.
So it's like the detective checking their notes before reinvestigating a clue.
Exactly.
And this prevents us from getting stuck in those loops.
Yeah, it makes it way more efficient.
So we have a function and this memorization table.
Mm-hmm.
Can you give me like a pseudocode example of how that would look?
Yeah, so the minimize extra function.
I could take the starting index as input.
Mm-hmm.
It would first check if we're at the end of the string.
Okay.
If we return 0 extra characters.
Right, because we've used all the letters.
Yeah.
Okay.
Then we check our memoization table.
Right.
If we already calculated this,
Mm-hmm.
we just return the stored value.
Gotcha.
If not,
Yeah.
we iterate through all the possible substrings starting from that index.
Okay.
And for each substring, we check if it's in the dictionary. If
Right.
it is,
Hmm.
we recursively call minimize extra
Okay.
for the rest of the string.
Okay.
And we keep track of the minimum
Right.
extra characters we encounter.
Okay.
And then finally, we store that minimum value
Mm-hmm.
in the memoization table.
Wow, that's a really elegant way to do it.
It is.
So that's brute force and top-down dynamic programming.
Yeah.
What else?
Well, there's also bottom up.
Okay, bottom up.
Yeah.
Is that like building a tower brick by brick?
That's a great analogy.
Okay, I like that.
Yeah.
I'm excited to hear more. Yeah.
About that one.
Yeah. So instead of starting from the big problem and like breaking it down,
Right.
we start with the simplest pieces
Okay.
and we kind of like assemble them up to the final solution.
How would that work for this problem?
So imagine we have an array called minextra,
Okay.
and it stores the minimum extra characters needed to cover the string
Okay.
up to a given index.
So each entry is like a position in our string,
Exactly.
and the value is how many extra characters we need to make valid words up to that point.
You got it.
Okay, cool. And we fill this array from left to right,
Okay.
starting with the simplest case.
Okay.
So we start by initializing minextra at index 0 to 0.
Okay, because an empty string has no extra characters.
Exactly.
Cool. Yeah.
Then for each index,
Okay.
let's call it, right?
Yeah.
From 1 to the length of the string.
Okay, so we're walking through the string.
Yep.
Index by index.
What we do is first we make like a pessimistic assumption.
That the character at index right is an extra character.
Okay.
So we set min extra at right to min extra at right minus 1 plus 1.
So we're saying, like, worst case scenario, this character is extra.
Exactly.
So the minimum is one more than what we had before.
And then here's the key part.
Okay.
We iterate through all possible starting indices
Okay.
to the left of right.
Okay.
Let's call it left.
So for each right index,
Yeah.
we're checking all the substrings that end at that right.
Exactly.
Okay.
And for each left index, we check if the substring from left to right
Okay.
is a valid word in our dictionary.
So we're trying to find words within the string that end at that right index.
Exactly. And if we find a valid word, we update min extra at right to be the minimum between its current value and min extra at left minus 1.
I see, because if it's a valid word, we don't need to count those characters as extra.
Exactly.
We just need to look at the minimum extra characters we had up to the beginning of that word.
Exactly. And by going through all possible lefts,
Right.
we make sure we find the best way to split the string.
That's really smart.
Yeah, it's really efficient.
So that's bottom up. Then brute force top down, bottom up.
Yep.
What else?
We have one more trick up our sleeve.
Okay.
Tries.
Oh, yeah. I love tries.
They're like super efficient dictionary.
Yeah, like phone books.
Exactly.
You can search for words so fast.
Yeah, they're great for prefix-based searches.
So how can we use them to minimize these extra characters?
So we can combine tries with our dynamic programming approaches.
Okay.
The try can help us quickly check if a substring is a valid prefix of any word in our dictionary.
Okay. I see how that would be useful.
Yeah.
Can you walk me through it?
Yeah. So first we would build a try from our dictionary.
Okay.
Each node in the try is a letter.
Okay.
And the path from the root to a node represents a prefix.
Okay.
And some nodes are marked to indicate if that prefix is also a complete word.
So if we had cat, car, and catch, they would all share the prefix K.
Exactly.
Okay.
Now imagine we're at some index in our string.
Okay.
Using the try, we can quickly check if the substring starting at that index is a valid prefix of any word in the dictionary.
So we can move down the try.
Yeah, one character at a time.
Matching the letters.
Exactly.
What if we reach a node that is a complete word?
Then we know we've found a valid word starting at that index.
Cool.
And then we can update our dynamic programming table.
So the try is helping us check if substrings are valid prefixes.
Exactly.
And that helps our dynamic programming.
Yep, it avoids a lot of unnecessary comparisons.
I like it.
Yeah, it's especially helpful with large dictionaries.
Okay, so we've done brute force.
Yeah.
2 dynamic programming approaches. And now tries.
Yep.
You mentioned one more earlier, though.
Oh, right.
Backtracking.
Backtracking.
How does that work?
So backtracking is another approach we can use to solve this problem.
Yeah.
And it's especially powerful when we combine it with memoization to avoid those redundant calculations.
So it's like we're exploring a maze.
That's a great analogy.
We try different paths.
Yeah.
If it doesn't work, we backtrack and try another one.
You got it.
Okay.
And we don't want to keep revisiting the same paths over and over.
Right.
That's where memoization comes in.
Our detective's notebook.
Exactly.
So we can store the results of those subproblems.
Yeah.
So we don't have to keep recalculating them.
Exactly.
Okay, cool.
Yeah, it's like we're trying every possible way to split the string into words.
Right.
And if we hit a dead end, like we can't form valid words anymore.
Yeah.
We backtrack and try a different path.
And the memoization table prevents us from recalculating all those subproblems over and over.
Yeah, it makes it way more efficient.
Can you give me an example in pseudocode?
Yeah, so let's say we have this function backtrack minimize.
Okay.
And it takes the string, the current index, the dictionary, and our memoization table as input.
Okay, so this is like our explorer going through the maze.
Exactly.
Like,
so inside this function, first we check our base cases.
Okay.
So if we've reached the end of the string, it means we've successfully split the whole string into words.
And we return 0 extra characters.
Exactly.
We also check the memoization table.
Yeah.
If we've already calculated the result for our current index.
And we just return that.
Okay. Well,
if not, we initialize a variable.
Okay.
Let's call it min extra to keep track of the minimum extra characters we found so far.
Okay.
And we set it to the length of the remaining string.
So that's our worst case scenario.
Yeah. It's like saying all remaining characters are extra.
Right. Okay.
And then we iterate
Okay.
through all possible substrings, starting from our current index.
So we're trying to find a word
Yeah.
to start our split.
Exactly. And
Right.
for each substring, we check if it's a valid word.
Right, using the dictionary.
Yeah.
If it is a valid word, then what?
We recursively call backtrack minimize on the remaining substring, passing in the updated index.
Okay.
And the result of this recursive call is the minimum extra characters needed for the rest of the string.
Okay.
So we add that result to the current substring length, and we compare it to our min extra.
And if it's smaller,
yeah,
we update min extra.
Exactly. So we're always keeping track of the minimum.
Right.
And then before we return from this function, we store min extra in our memoization table.
Right, so we don't have to recalculate it.
Exactly.
Okay. I think I get it.
So that's backtracking with memoization.
Yeah, that's a lot.
It is.
But I think I'm starting to get it.
So we've covered a lot today.
Yeah, we did brute force, dynamic programming, top-down, bottom-up tries, and backtracking.
It's a lot of different approaches.
It is.
But I think they all have their own strengths and weaknesses.
Exactly. And it just depends on the situation.
Yeah, like what are the constraints to the problem? What's the size of the input? You know, how much performance do we need?
It's like choosing the right tool from a toolbox.
Exactly.
So hopefully this episode has give everyone a good overview.
I think so.
Of how to tackle this problem.
It's a fun one.
It is.
Yeah.
And be sure to check out the show notes.
Yeah, we have links
for more resources.
To some great resources on these topics.
Yeah, if you want to dive deeper.
Yeah.
And
thanks for joining us.
Thanks everyone for listening to AI Codecast.
Catch you next time.
We'll see you on the next one.